I reckon it's 10:15, so welcome everybody. So my name's Neil. I'm going to be talking about OSGi, Java 9, and the future of modularity on the Java platform. So let's talk about Java first of all. Java has a problem. Java is getting larger. It's been getting larger since its first release, and at this stage it's actually quite overweight. So Java needs to go on a diet. Here is the graph. So I got these numbers basically from the download sizes for the official JDK releases from, obviously originally this was Sun and then later Oracle. And you notice here, of course, that the earlier versions, there was no Sun official version for Linux or anything other than Solaris. But you can see a very definite upwards trend here, particularly with the macOS versions here, are very large indeed, over 200 megabytes for Java 8. So that's pretty big for a base platform. Now, who cares about that? Well, the enterprise doesn't really care about this. And that's partially why this problem has happened. The enterprise guys, they're dealing with big servers, disk is cheap, memory is cheap, and the main competition for years on the enterprise platform has been .NET, and .NET has been following basically the same kind of trajectory. So we haven't really had a compelling need to slim down the Java platform. But these new platforms, IoT and so on, they definitely do care. You know, you've got these Raspberry Pi Zeros and Arduinos now. Okay, Java can't run on an Arduino yet, but these platforms have very little memory. So every megabyte that you can save in terms of memory on one of these things, if you're scaling out to hundreds of thousands of devices that you're deploying into your market, then you're saving a lot of money. Also on these platforms, our competition isn't just .NET anymore. It's these much smaller and sometimes more agile, or at least perceived as agile platforms like Node, Go, Rust, Swift, and so on. So the Java modularity story is quite a long one. It started in the late 1990s with OSGi and JSR 8. So OSGi was originally something called the Connected Alliance, and it was seeded with JSR 8. Now, JSR 8 never actually became an official spec, but that was the start of what became OSGi. The OSGi Alliance was formed. Release 1 of OSGi came out in 2000. And these days we're using OSGi Release 6, and we're working on OSGi Release 7 to be out next year. But we were never able to modularize with OSGi the JDK itself. So we could never really do anything about those increasing download sizes of the JDK and memory footprint of it. And there's various reasons for that. Now, some of those reasons were political and commercial, to do with some of the relationships between the different community members within Java. But I'm not really going to be talking about politics and commerce here. I'm going to be talking about the technical reasons why this has happened. So OSGi was not used to modularize the JDK. There were several aborted projects kicked off by, first of all, Sun and later by Oracle, that started in the mid-2000s. Several of these projects started and ran for a couple of years and then failed or were killed off. So does anybody remember JSR 294, the so-called super packages spec? Yeah. That was a bad idea. Later on, JSR 277, the Java module system, that also ran for a few years and then died. Now we have JSR 376, the so-called Java Platform Module System, or JPMS. And that's the module system that I'm going to be talking about in connection with OSGi in this talk. So JPMS was seeded by this prototype project called Jigsaw. Jigsaw is probably what you've already heard of. Jigsaw was a project that was targeted for Java 7. So it was meant to come out in 2011 as part of Java 7, 5 years ago. It slipped to Java 8. It held up Java 8 for a little while, and then it slipped again to Java 9. Java 9 is currently slipping. Java 9 is delayed by 1 year so far. Java 9 is going to be coming out in September 2017, according to the current schedule, which was just updated last month. So clearly, the problem that they're trying to solve here is not trivial, because it's currently running 6 years late. Remembering this was originally targeted for 2011 and will not be coming out until 2017 at the earliest. But it is coming out. It is coming in Java 9, probably. And JPMS's primary goal is to modularize the JDK. So to cut down the pieces of that big, heavyweight monolith JDK. But it doesn't limit itself to just the JDK. It can also be used to modularize libraries and applications. So how does that affect OSGi and Eclipse? I know we're at EclipseCon, we have a lot of Eclipse users here. How does that affect existing users of OSGi and Eclipse? So I'm going to talk about some basics of how these two systems compare, and then we're going to talk about how we can work with them together. So a quick definition of a module, and this is just my informal definition. So it's a unit of encapsulation that communicates with other modules through agreed contracts. Keywords being encapsulation, so hiding of internal details, communication, and contracts. So what is not a module is a sort of traditional monolithic Java application, this big ball of mud with loads of jars on the class path. So a monolithic Java application has no encapsulation between these things called jar files, which are units of deployment, because any type can interact with any other type on the class path. The communication between those so-called modules or within the pieces of that monolith is ad hoc and tends to be uncontrolled. Contracts, in terms of Java interfaces, they may be used, but not very rigorously. So let's talk about encapsulation or isolation. This is the fundamental problem you have to solve if you want to build a module system. First of all, you have to divide things up. You have to build walls. But the height of the wall that you build is not a fixed thing. So isolation is a continuum. The principle of isolation is freedom from interference from other encapsulated objects. And it has a cost. Every little bit of isolation has some cost. Now, probably the least isolated thing you can think of is writing the entire code for your application in a single Java method and using gotos to hop in between that method. Now, Java has a 64K limit to the length of a method, so that's not very practical. But there's many other reasons for not doing this. What's the most isolated? Well, I guess it could be if Tesla or SpaceX managed to put a data center on Mars, right? Because that data center on Mars will be protected from any catastrophe, such as an asteroid hitting the Earth, and therefore there will be no interference between those two things. And in between, we have lots of other points. We have VMs, we have physical servers, we have Docker containers, and so on. So OSGi and JPMS, they both live on this continuum, and they provide a basic level of code isolation. What they don't prevent is things like a module crashes the JVM because it consumes all the available memory, or because it creates 1,000 threads, or more than that, or even that it calls system.exit. And we can turn on the security manager and prevent system.exit being called, but OSGi and JPMS do nothing to prevent this kind of thing. What they do both prevent is modules, or in OSGi bundles, from accessing the internal types from other modules. So how does OSGi achieve this isolation, first of all? Excuse me. OSGi achieves isolation with the concept of visibility. OSGi creates a class loader per module, per bundle. So each bundle has a class loader, it has a class space. So the set of classes that are visible to that module. And it's equal to the private contents of the bundle, so all of the classes and types that are inside that bundle one, and anything that it's importing from anywhere else, but doesn't include any private types within other modules, for example. So in this case, bundle one cannot see the types that are in this bundle two's private types here. Now, when I say it can't see it, from bundle one's point of view, it's as if it didn't exist. And so if bundle one were to try to go ahead and load one of those types, it would give us a class not found exception, as if that, again, that type did not exist at all from bundle one's point of view. JPMS is different. JPMS modules on the so-called module path live in a single class loader. So when you put a bunch of modules on the class path, on the module path, have to get used to saying that, you put a bunch of these J modules, they will be loaded by the system class loader. Now what that means is they all live within the same class loader and they can all see all of the other types within that class loader. But JPMS adds a level of access control. So access is what we're familiar with when we try to do something like call a private method on a type that we're not allowed to call. So JPMS adds an additional access layer. So if there's a private type over here, and when I say private, this is a non-exported type. It could include types that have the keyword public on them. So it's an interesting change of the semantics of public, because we now have public types that can't be accessed because you're outside the module. So if I'm over here in module 1, I don't get to access those types in module 2, although I do have visibility of them. And quite curiously, if I'm in module 1 and I say class.forName to get a class from module 2, I will be able to get that class. That's allowed. But as soon as I try to do anything with that class, if I call new instance on it, for example, I will get an illegal access exception. So that's the access control, the isolation level that's added by JPMS. Yes, Lars?
So also with this, I cannot use a reflection to call any methods on these classes or instances?
Well, if you can't get the object, yeah. So new instance is not allowed, any static methods are not allowed, and obviously any instance methods, you can't get an instance, so it's irrelevant. And incidentally, in case you were wondering, can I just say set accessible true? You know, the classic old, let's take a private field and turn it into a public field by saying set accessible. No, you can't. That throws an exception as well, inaccessible object exception. So there are some implications for both of these approaches. The implication in OSGi is that, for example, this works. I can have two bundles that have overlapping private contents. So let's say both of these modules are using Guava in this case. So I've got some package name here from Google Guava. And each of them has taken a copy of a package into their private contents. Now, why would you do that? It's actually a very useful technique. It's called static linking. And in certain cases, I can do this to avoid things like external dependencies, avoid versioning issues, and I can make sure that the version of Guava that I get in my bundle is always the version that I've tested against. And I'm not going to get the version that somebody else on my class path wanted. Incidentally, there's a little legend here. So these gray rectangles are private packages, non-exported packages. So I can do this in OSGi. I can also do this in OSGi. So the black rectangles, these are the standard notations from the spec, by the way. The black rectangles are exported packages. So I can have an exported package, orgexample API, and orgexample API twice. Two different versions, although they don't have to be. That's the practical use case for this, is having multiple exports of the same package, but with different versions. And that's allowed. That does add some complexity. Right, so being able to do this doesn't come for free, and you sometimes have to resolve some interesting situations. But the fact is it's possible. and is very helpful when we're not able to reduce the set of our dependencies down to a single version of every library. And we can even do this. So here we've got, so the white rectangle is an import. So here the bundle has got A, B, C. B is being imported from bundle 2. That's an export from bundle 2. Bundle 2 is also importing C, which is exported from bundle 3. And by the way, bundle 1 also had a C, right? So we've got overlapping privates here. We've got some matching classes. Now, bundle 1 here is seeing the packages A, B, and C. Bundle 2 is seeing the packages B and C, and bundle 3 sees the package C. But bundle 1 sees the correct C, right? So it's not going to be accidentally getting this C over here on the right, which it's not compatible with, even though it's exporting something which is kind of exposed to it in some way. But what doesn't work in OSGi so well, and this is the source of a great deal of pain, is this kind of thing. So I've got two bundles over here exporting an API. This bundle on the left is not importing that API, but instead it's doing reflection. Class.forename, and then something from org.example API. Now what's wrong with that? Why can't I see org.example API foo? Well, the problem is there's multiple candidates. In any modular world where we have the potential for a type to exist in more than one place, I can't just go and ask for a type by a single name. I have to specify also where it's going to come from. So the type name is not unique, but if we specify the bundle that we want to get this from, then we're fine. Now this does create problems in OSGi because there's many libraries out there in the very, very wide Java ecosystem that make assumptions. They make assumptions that you can just say class.forename and it will just work. And unfortunately, in these situations, the OSGi class loader is forced to just guess. And some of the time it'll guess right, and some of the time it'll guess wrong. And that's when you get bugs in your code. So this is probably the biggest source of frustration for new OSGi users, well, even experienced OSGi users. But what exactly are we to do about this? We really have to improve this situation with people assuming that classes come from a single place. So this is part of the motivation for why Jigsaw and JPMS does what they do, because there are lots of these assumptions in the JDK. Parts of the JDK assume that all other parts of the JDK are visible within the same class loader. And so that's why they've come up with a design where you can have multiple modules within a single class loader. The consequence for JPMS, though, is that this doesn't work. So I've used blue as a JPMS module to contrast with an OSGi bundle. So same situation, Google Common Base in both of these modules now, but this will not work. If I try to install both of these modules into my module path, I will get layer instantiation exception, package blah in both module A and module B. So these two modules are unable to coexist because of their private contents conflicting. So if I want to work out whether two modules are going to work together, I can't just look at their exports and their declared metadata. I have to look at all the details inside them as well. Now, in JPMS, we can create class loaders, and we can map class loaders to modules and start doing our own class loading. So in other words, we can run OSGi in JPMS. But JPMS isn't really helping us with this situation out of the box. Yes, Martin?
Just a question. I heard a presentation where they said there's a mechanism above modules called layers.
Yes.
And then something like application servers are doing inside to create layers, and layers could do that.
So yes, you can create a layer, and in your layer you can manage your own class loaders. And so you create a mapping of modules to class loaders, so that you then essentially create a class loader per module. So yes, you can do this, but in my opinion, you're halfway to implementing OSGi as soon as you're doing that. That's essentially what I'm saying. As you said, like modules and class loaders are orthogonal in one sense, but you kind of need to do it, and somebody's got to do it. Incidentally, even if you create your own class loaders, you can't do this. You can't have multiple exports of the same the same package, or example API, within the same layer. You have to create multiple layers in order to do this. So multiple exports of the same package. Okay. So that's isolation. But isolation is just the first thing that you need to do. You next need to work out, well, how do you actually get back to communicating? So you've separated everything apart. How do you start communicating again? And as they say, any fool can build a wall. But working together is harder. So once you build the walls between the modules, how do you then form the communication and the cooperation between those modules? And do it in a controlled way so you don't get back into the same mess you were in before. So we do this by sharing packages. Both JPMS and OSGi share packages between modules. In both cases, any packages that are not explicitly exported are private. So in OSGi, it looks like this, export package. In JPMS, it looks like this, exports, and then the name of a package. Looks very similar. In JPMS, this thing is a moduleInfo.java, and it gets compiled to a class file called moduleInfo.class. This is an OSGi manifest, and it would typically be generated by a tool like BND. So in OSGi, the complement of exporting is importing. So if we export something, we want to import it. And that creates a so-called wire. And across the wire, class loading requests can be delegated. So if in a need for a type in example OSGi API arises, then the class loading request gets delegated across to B. OSGi also supports something called require bundle. And require bundle has the effect of importing all of the exported packages of a named bundle. Require bundle is deprecated. Now, I know there are some Eclipse developers in the room who may be disagreeing with me. You're wrong. Read the OSGi spec. Require bundle is deprecated. You should never use it. Well, almost never. It's the almost that's the tricky bit, isn't it? But it's deprecated because it creates really bad situations. For example, I can't refactor with require bundle. This is what I want to do if I want to refactor and I've used import package. So I've got two bundles here. B is importing two packages from A. And then I want to do an operation on A. So somebody comes along and says, look, these two things are not really directly related. We should separate them out. So we separate them into two different bundles, A and A prime. B continues to work because it's still importing those packages from the same, in the same way, but from different places now. With require bundle, B was previously exposed to these two packages, and now, after this refactoring operation, B is only exposed to one package. And we have no real idea whether B was using that org.bar package or not. And so it's never really safe to do this operation on A, this refactoring operation on A, because we don't know whether it's going to break bundle B or not. JPMS only supports requires. So it's essentially equivalent to require bundle. And it has the same problems. I can also say requires public. And requires public means re-export. So I can say requires example API and requires public example foo.api. And this foo.api is re-exported by my module. So anybody depending on module B will also get the package example foo.api. We have a very similar re-export in require bundle in OSGi. Okay. Versioning. OSGi supports versioning of bundles and packages. So we export packages, for example, with a version like 1.01, and we can import packages with a version like 1.2. The tooling that we use detects what range to use here. So we shouldn't be manually writing these ranges. We should allow the tool to determine, okay, you've consumed an interface, you're not providing the interface, so you can have a nice wide open range from 1 to 2. Now, it takes a little long to explain why that's 1 to 2 and not 1 up to 1.1. There's been other talks about that at previous Eclipse cons. But the point is that that stuff is controlled and generated, managed by the tooling. So org.foo with 1 up to 2, it can import that one. It cannot import that one because it's the wrong version. The 2 here is exclusive. JPMS doesn't support versions, essentially. JPMS doesn't provide versions in module info. I can't write the version of a module in module info. The module info class does have a version attribute in it, in the class file, but that doesn't come from the source code. It's a very curious thing. It comes from a command line parameter on the jar command. So the jar command appears to be rewriting the class file when it builds a jar. So the version, although we can provide it by passing this command line when we build a module, it's not used anywhere. There's no support for multiple versions of a module. And remember, you can't have overlapping packages, so how would that ever work anyway? And version selection by the module system is completely out of scope for JSR 376, for JPMS. So the expectation in JPMS is that somebody, probably a tool like Maven or Gradle, will be able to construct sets of modules that work together by analyzing their metadata and their private packages and working out whether these modules will work together or not. And that does mean that they have to reduce those set of modules so that there can be no more than one version of any particular library. Now, I don't know if anybody's ever built with Maven and tried to work out all the excludes they need to get so they only get one version of SLF4J on their class path. It's pretty painful. So Maven isn't very good at this at the moment, so it's going to have to get a lot better at it pretty quickly. Let's talk about dynamics. OSGi bundles can be dynamically updated, installed, and uninstalled. But if you're an enterprise developer, you probably don't care about that. And fair enough, that is a fair point. Most enterprise developers and production systems are not dynamically redeploying software without restarting the server. And that's fine, and nobody's forcing you to do that. And there are use cases where that is important. Again, I go back to IoT, where it's actually very, very valuable to be able to deploy a minimal change to your software, especially if you have lots and lots of devices deployed out on a low bandwidth, possibly intermittent network. So OSGi is one of the very few platforms anywhere that allows you to do that. But fair enough, you may not want to do that. But dynamics are very relevant as well in OSGi services. Now, an OSGi service represents the state of the real world. So I can create a service that represents the availability of a remote service, something I might want to invoke on the network. And I want that remote service to reflect the actual availability of the remote thing that I want to call. And that can change. Even in an enterprise scenario, things can change in the real world. I can even have a service that represents something like market opening hours. And again, that can obviously change. So OSGi is encouraging this robust programming model that allows us to write components that adapt as the state of services and the real world changes. JPMS dynamics, well, there aren't any JPMS dynamics. It's a fixed module graph. It can't be reloaded. You can create new layers on top of the current layer, but you can never change a layer once it's baked. Reflection. Now, this is the big one. Let's look at this OSGi scenario again. So remember I said I can't just say class.4name to get a random class from somewhere. What I can do is if I get hold of a bundle, so bundle A over here, somehow I get hold of the bundle. I've just omitted that bit of code. But then once I've got the bundle, I can say load class. I'm loading an internal type here, and I'm instantiating it, and I'm doing something with it. And that works in OSGi. That's allowed. Now, you note that there was no import of the internal API. It wasn't exported. And this is always possible as long as we know the type name and the bundle that it's coming from. And a major use case of this is something like declarative services. So in declarative services, we have component classes that we annotate with the app component annotation. the build tool creates an XML file inside the bundle, and the XML file is declaring the name of an internal class here. And then at runtime, the service component runtime, SCR, creates a component called foo, and it wires it up to services for us and manages the object for us. So this is the really important, this is the most widely used programming model in OSGi. Now you might ask, doesn't that break encapsulation because I'm loading internal types? Well, it's debatable, but I would say no. From a practical sense, it's not breaking encapsulation because the origin bundle is having to explicitly declare the type that it wants you to load. And otherwise, from the outside, you don't know what that type is going to be. So this reflection, this reflective access to a bundle is always possible at runtime. And yes, that could be used to do bad things. But if you do bad things like that, you can't go and claim that you didn't know what you were doing. Or you can't do it by accident, which is the big problem with uncontrolled dependencies. So other use cases for this would include dependency injection frameworks. I mean, all of them. Spring, Juice, all of them. Object relational mapping, Hibernate, JPA, CDI. CDI belongs with the dependency injection. Serialization frameworks, JAX-B, protocol buffers. And the Eclipse extension registry. For the Eclipse developers here, plugin.xml, you know that it names classes, and those classes are going to be loaded by the Eclipse extension registry at runtime. So in other words, most of our critical infrastructure relies on the ability to reflect on internal types within bundles, within encapsulated modules. In JPMS, if I reflect on a module, I will automatically get something called a read edge, which becomes like a runtime wire into a bundle. So I automatically get a read edge to a module as soon as I reflect on it. But the private packages remain inaccessible, period. I mean, I cannot access those at all. I can't call set accessible. They are locked out. So I can't implement all of these things, ORM, dependency injection, serialization, and so on. And this is probably the biggest area of contention and discussion on the JSR 376 mailing list. And here's a link to an issue that describes it and current proposed solutions. The first non-solution to this is to use services. Now, this is the service loader approach that's existed since Java 6 and is being extended in Java 9 to support services coming from modules. So service loader has a privileged access to named types within the module. But it doesn't help us because the services in standard Java are very limited. I've got no lifecycle control. I always get the same instance. I can't do dependency injection. I just get an object and that's it. And also, if I had a DI module, something like Spring here, I'd have to say, this is my thing that's providing something to Spring. I would have to say provides, there's my interface name, and then there's my implementation. But Spring or similar dependency injection framework would have to do uses example API foo and everything else that it might ever want to use. And of course, it has no idea what that might be ahead of time. So that's not a solution. Second solution, export and be damned. Just export all the packages that might contain code the types that need to be loaded. Well, that will work, but you've just completely broken encapsulation. You've thrown away all of your encapsulation, both at build time and at runtime. So at build time, all of those private types are now public API. So you export that API, and you just hope that nobody depends on this. Second possible solution, qualified exports. So in JPMS, there's one thing they can do that we can't do in OSGi is a kind of a friends export. So I export a type to a specific requirer. So I can say exports that type, that package to Hibernate. But bad luck if you're using a different JPA implementation like Eclipse Link. That's a problem there. A possible solution, dynamic exports. So Oracle proposed this, and they implemented it in the early access releases of Java 9, and then they killed it only last month. which I can imagine created a bit of pain for the guys who'd written a book about this already. But the idea is that exports can be effective at runtime only. So export's dynamic. So this is a package that you can reflect on at runtime, but you can't depend on in the compiler. And the problem there is you have to explicitly list every package that might want to be accessed this way. And you just have to hope that you got them all. The current proposal for this from Oracle is so-called weak modules. So a weak module, which is declared as weak module like that, is a module that has no private packages at all. Everything is exported. You don't explicitly export anything. You cannot explicitly export everything because everything is exported by default. So this is envisaged by Oracle as a kind of a transitional step, a migration step towards full or so-called strong modules. The question is, if we're using DI, can we ever really get off of weak modules? Can we ever get rid of these weak modules? I don't think we can. Another possible solution which comes from a community suggestion was this idea of a privileged module. So rather than weakening every module that might need to be accessed by a dependency injector, instead privilege the dependency injection framework itself and allow it access to the internals of other modules. Thank you. So I've gone a bit over time, so I'm going to quickly fast forward to interoperability. So can these things work together? The first answer is yes. Java 9 is backwards compatible. There are some bugs at the moment, but you can run OSGi applications on Java 9, and that must be possible because Java 9 will support all applications that use standard Java, and OSGi uses only standard Java APIs. The compatibility issues here are the standard ones for any Java code, so anybody that's using something like Sunmisk Unsafe, for example. Can we do better? Yes, we can. So in OSGi, the standard way of declaring your dependency on the platform is this thing called an execution environment. So I declare that I depend on J2SC 1.8. And that's a bit of a mess, but that's generated by the tooling again. And this bundle will now only resolve if it happens to find itself running on Java 8. So it can't accidentally access things that it shouldn't be able to if it ends up running on Java 7. And then we import package for everything else outside of java.star. So on Java 9, the import package for everything outside of java.star works fine, but the execution environment concept is probably obsolete. We have to move away from that because we can't any longer have a monolithic platform with a single version. So we need to depend on platform modules. So we need to be able to depend from OSGi onto JPMS modules in the platform. So my proposal, and this is very informal, there's no guarantee the OSGi is going to do this, but it's a proposal that I have, is something like a header require platform module and then the name of a Java module. And so what that should mean is if you have this in your OSGi manifest, then this bundle should not resolve on an OSGi platform, on a Java platform that doesn't have that module in it. And furthermore, you can take a bunch of these modules that have these declarations and construct a runtime that contains only the set of JPM modules that you actually need. And it would look like this. So modules depending on JPMS modules. I have a proof of concept. I'll show that briefly at the end because I really have timed this poorly. So I will tell you that it does work and the code is here. You can run this. And I've simulated this new header by saying require capability with a J module. I've invented this J module capability that you can depend on. And so that worked. I was able to resolve my bundle on a platform that had that module, and it doesn't resolve on a platform that doesn't. So as I said, I'll skip the demo, possibly come back to it. So next steps, use JDEP to create a minimal platform and integrate those tools into BND and BND tools. That was unidirectional dependencies. There is some potential, perhaps, to do multi-directional. Now, it's very complicated. and it requires lots of messing around with internals of OSGi and probably has to be done by the framework implementers. So Tom Watson, who's the lead of Equinox, has done some experimental code in doing bidirectional dependencies, so jigsaw modules depending on OSGi. This may work, it may not. It will also require some additional features in JPMS, which may or may not be added in the final release. Okay, yesterday I was added to the JSR expert group. So I'm now a member of the JSR 376 expert group. So I'm hoping to represent the OSGi community. So if you're an OSGi user or developer, I would like to have any concerns or questions or something you think should be in JPMS to enable OSGi, or maybe you don't care about OSGi, let me know about that as well. But if so, why are you in this talk? But still, if you have any concerns about JPMS and ideas, please do contact me. Quick conclusion. Adding JPMS to an existing 20-year-old platform is very difficult. JPMS did what was necessary to modularize the JRE without refactoring it. OSGi couldn't have done that. But the choices that JPMS made in order to do it have negative consequences. So why suffer those consequences when we're not inside the platform itself? So my takeaway message is JPMS for the JDK, OSGi for everything else. Now, a quick little afterword for just the people in this room. This won't go on the conference slides. JPMS does actually remind me of something, and I'm cursing Tim Ward because he took away my punchline last night. But JPMS kind of reminds me of Brexit. So I didn't vote for it. Nobody knows what it's really going to look like. Probably won't work. Huge distraction from actual important stuff. Can't be stopped.